Want to welcome everybody, participant to this webinar. This is one of the many webinar GMI is arranging since the COVID time started, and we decided to proceed. Even we are back to normal life, and luckily we have a lot of chance for face-to-face meeting and for face-to-face seminar, but still through the webinar, the online webinar, we have the chance to reach a lot of people and to share our knowledge with a lot of people. Today, as said, we deliver many webinars on different subjects. We touch subjects relevant to functional safety, to cybersecurity, to intrinsic safety, even a webinar on application of GMI product. Today, I have the chance, I'm proud to be here with Bob, one of the most knowledgeable person I know when we deal about hazardous location and hazardous installation and application. So let's go ahead because Bob has a lot of interesting things to share. I just only want to give an introduction. First of all, introduction to this webinar, just few service information. Let me say, we are going to record this webinar, and this webinar will be then available on our YouTube channel. So if anything is not clear or you want to review that, you have the chance later on to go through. On the YouTube channel, you also find all previous and all future webinar that we are going to provide. Very interesting, as said, on different subjects. You will get a copy of the PDF presentation. So you will get an email with the PDF of this presentation. You have the chance through the question and answer button. You have the chance to raise questions in case of need. While Bob will do the presentation, I will monitor the question and answer, and I will stop him in the right moment to provide the relevant answer. And last, let me say one thing. We have also prepared a question and answer section based on the questions that you raised during the registration process, or we are including also some interesting question which was raised in previous webinar. We want to share with you also this kind of point. Again, you will have the copy of the presentation, so you will go through the various detail. Let me just say a few things about GMI. GMI is a manufacturer of field equipment, field interface, such as instrument safety barrier, isolator, safety relay, power supply systems, and something similar we will see later. You find GMI equipment in most of the automation package, DCS, ESD, fire and gas, burner management system. And we cover several industrial sectors, like mainly oil and gas, chemical and petrochemical, but food and beverage and pharmaceutical as well. We have, as GMI, 40 years experience dealing with intrinsic safety and functional safety as well. We do everything here in Italy, and but of course, we are available worldwide with our commercial office and with our support that we can provide worldwide. Can go on.
There we go.
Yes. Yeah. As said, we are in Italy. The main company, the production side is in Italy, but we are available almost all over the world with our subsidiaries or with our partners, whether they are agent or distributor. Yeah, of course, we do, as said, we do everything here in Italy. We have a state-of-the-art technology. One important step, which I would like to highlight, is that we test everything 100% before something leave the factory. And that's why we are so confident about the quality of our product, that we deliver our product with 5 years warranty. Let's go ahead. Yeah, as said, the quality is one of the most important topics, since we deal with the safety, whether it is intrinsic safety or functional safety. We are in somehow responsible to protect the human life, to protect the assets of a company as well as the environment. That's why we hold several kind of certificates, including all the necessary certificates which are demanded, which are requested locally. So you can see here a lot of certificates starting from the CE, mainly for Europe, as well as UL, FM for United States, and we have certification for the UAE, for India, for Brazil, and so on and so on. So I would say almost all countries are covered. Here in one page, we just show our portfolio, our range of product, which is ranging from ES barrier to loop indicators. Last bullet, and it is including safety relays, as isolator, power supply systems, and so on and so on. All of these items, let me say, cover either the intrinsic safe aspect, or the functional safety aspect, or both of them. So you can find intrinsic safe barrier which are seal-free, which are suitable for seal-free application, for example. Last bullet, it is I want to show our expertise. No problem, no problem. Our expertise in intrinsic safety and seal and the functional safety. That's in fact what we provide as a service, consultancies to our customer, or webinar, or even training, kind of training, which then would provide a formal certificate to the participant. Next slide is just a list as an example of our kind of customer where GMI is in somehow already installed. So we have, of course, system vendors, we have EPC contractor, we have OEM, as well as, of course, end users. And yes, I think this was as promised, I was short. This was my last slide before to handle the conversation to Bob and to enter into the detail of, yes, I missed to mention, today's webinar title is Fundamentals of Intrinsic Safe. So,
all
Bob.
Right. Thanks, Mauro. I appreciate it. Thank you very much. I hope everybody can hear me. Welcome. Again, I want to extend the welcome just like Mauro has. Fundamentals of EX. There's a lot of information in the EX world. And so obviously we can't cover everything in 30, 45 minutes or so, but we'll try to kind of hit the highlights of the important stuff that's really fundamental, right? Certainly if we have questions going on, and I understand that many of you, this may be a repeat of what you've already heard, or hopefully maybe I can share a little bit of information that maybe you're not familiar with. As Mauro said, we also do training, we do competency training here in the US, and we work with GMI worldwide to be able to provide these types of formalized training programs under the IEC EX COPC scheme. So today we're just going to talk a little bit about some of the fundamentals of EX. And of course, as Mauro mentioned, GMI is obviously in the oil and gas industry, and we think of EX as something that is primarily focused on the oil and gas industry. But a lot of people are not as familiar with the fact that there are significant amount of EX applications and environments that we're going to find outside of oil and gas. So certainly pharmaceutical industry, the pulp and paper industry, the marine transport industry. There's lots of different industries that are out there in which flammable environments can occur. And so the types of flammable information or the types of environments that we're going to see are typically either gases, vapors, and mist. That's what we would traditionally think of, flammable gases of some sort. Combustible dust, those are typically those environments in which we would find either in grain elevators or some processing, food processing. Pharmaceutical also have dust applications, and solid particles, these are actually in some process areas where we can actually have more of a dust layer. It's not so much combustible dust, but maybe fibers and flyings, things that can actually ignite. So these are the types of environments in which the EX standards and the EX requirements come into play. And one thing I want to highlight too is that everything that we're really talking about is based upon the IEC 60079-79 standards. And many of you are, I know, located within Europe, but you're located in various parts of the world, including the United States and Canada. What most world countries have done is that they've taken the IEC 60079 standard and incorporated them into their own country-specific standards. So a lot about what I'm going to be talking about here today will apply even outside of markets in which you're not necessarily following IEC directly, but the IEC is kind of the foundation document. Those 60079 documents are the foundation for the EN standards, the ASNZS standards, in the UL standards in which we've adopted 60079, as well as other country-specific standards. So again, a little bit about explosive atmosphere types. Flammable and combustible liquids can produce gases or vapors, which are also combustible, right? These gases can be easily ignitable and are very dangerous, given that they can spread quickly and widely. I just literally saw a video this morning that was published on a report from the National Transportation Safety Board here in the United States on a pipeline explosion from 2019. The video is very hair-raising. Unfortunately, one person passed away from the explosion. But these types of explosions that take place, they happen almost on a daily basis, unfortunately. But we somewhat get, we get, I don't know, immune to it because there's so many other worldwide events going on. So we sometimes just say, oh, it happens, but it does happen significantly, and it happens almost on a daily basis. So we need to try to make sure that we think about this in our own particular projects and jobs and our responsibilities to kind of keep this in the back of our mind. Any flammable liquid that are at or above their flash point will give off a combustible vapor. So the flash point is that temperature in which a liquid becomes a vapor, if you will. So that's different from ignition temperature. Flash point is the point in which, again, it will give off enough ignitable vapor to ignite. Because liquids then in and of themselves, flammable liquids, are not necessarily the issue. It's when they start emitting vapor in combination with air, that's when we have problems. See if we can go. Yeah, there we go. That's the temperature. Ignition temperature is the actual temperature in which that gas or vapor or dust will spontaneously ignite. So there's two different points to think about: flash point and ignition temperature. So combustible dust, where do we find those? They could be metal dust, carbonation dust, coal mines, right? Coal, carbon black. But we could find these types of carbonation dust in refineries as well. Coker units within a refinery are very much a dust hazard, right? And again, as I mentioned, flour, grain, wood, plastic, and chemicals are different types of combustible dust. So only dust with stable oxides will not be combustible. So keep that in mind. So when we talk about an explosion and talk about the fundamentals of EX, we basically, in order to have an explosion, we need to have three legs of a triangle. We've all seen this in some way, shape, or form, but we need to have a combination of a source of ignition, an explosive material, and oxygen or air, right? So when we have any one of those three legs missing, then we've addressed it in some way, shape, or form. But if we have all three of those legs present, then that's usually when we'll have an explosion under the right conditions. So the whole idea of EX protection is to try to eliminate or reduce or mitigate one or more legs of this triangle, if you will. So the question that usually comes up is, when we think about sources of ignition, obviously when we're talking about intrinsic safety like a GMI barrier, intrinsic safety, the whole concept is keeping that source of ignition below the minimum ignition curves of the flammable gas air mixture. So the way that we use IS, that's in effect, it's eliminating that source of ignition, right? But when we talk about other protection concepts, that's when we start looking at different methodologies to protect. But usually the question also comes up is, people think about sources of ignition generally as maybe electrical equipment. I'm in the electrical business. That's where I grew up. So I've always thought about things like electrical arcing and sparking. However, in reality, in many cases, a lot of these major industrial accidents are actually caused by other sources of ignition, such as hot surfaces. Exhaust systems that you find. The BP Texas City explosion took place because of a diesel exhaust system on a pickup truck that was located near a cracking unit that ignited the flammable gas. So that was a hot surface. Open flames, obviously, cigarette lighters, pilot lights, cutting torches, things like that. That's why we have safe work permits for using these types of equipment in hazardous locations, or we may require gas-free certification. Other things like mechanical sparks, cutting or grinding. People don't realize that certain tools, when we take certain metals and we drop them or rub them against another type of metal, can generate enough energy in which we have a spark. If we look at people that, videos or movies or anything else from old time where people are forming swords or anything like that, and we're taking an anvil and we're banging on it, doing all this, we're creating mechanical sparks. So obviously, hopefully not doing that in a flammable atmosphere. Stray electrical currents, electrical faults is certainly one of those big issues that we talk about. Another issue that doesn't necessarily always get thought about too much, but is static electricity, the buildup of static electricity. This could be from conveyor systems, flowing liquids, airstream leaks, agitators. All of these things can create static electricity, so we need to address that. And now that we're talking about using radio frequency, everything from lasers to communication, we have to be concerned. Is there enough energy in the radio frequency to ignite a flammable gas air mixture? Some of the other things, batteries, ionization radiation, ultrasonics, exothermic reactions. We all can probably remember about the massive explosion that took place in Beirut, where that was ammonium nitrate that was stored in a warehouse down near the port. And that was, in effect, an exothermic reaction that took place with the ammonium nitrate being stored next to fireworks that actually started to go off. And just the fire in and of itself wasn't enough to actually ignite that ammonium nitrate, but the buildup of heat and everything in a confined space ultimately resulted in obviously a terrible event. So again, we need to think about some of these other sources of ignition. And when we're in our facilities, when we're looking at equipment, don't just think about the obvious things. Look at some of the things that are maybe not so obvious. Or maybe if you're working in a facility and they say, hey, you cannot take this particular piece of equipment into a hazardous area, like your iPhone or a key fob or something like that, or even a flashlight torch. There's a reasoning behind that. It's because all of those devices potentially could be sources of ignition. So gases and vapors, primarily talking about gases and vapors, all gases and vapors have different ignition temperatures. And we categorize these in different groups. So using some of the most popular gases and vapors that we'll see in industry, things like hydrogen, you'll notice that hydrogen has a very, very high ignition temperature, about 560 degrees C. So it takes a lot of temperature to ignite hydrogen. And you see other gases down there generally quite a bit, significantly less, right? Hydrogen sulfide, for example, only takes 270 degrees in order to ignite, spontaneously ignite. So you would think that hydrogen sulfide is actually a much more dangerous gas than hydrogen. Well, gas grouping is only one factor in which we want to categorize these gases, and it's also based upon some other factors. The other factor that we take into account with regards to gas grouping is actually the ignition energy. This is how much energy it would actually take to ignite these gases and vapors. So if you notice on this slide, notice that hydrogen, even though it took a very high temperature in which to ignite, it doesn't take an awful lot of energy. We're talking 19 microjoules worth of energy. To give you an understanding of how little 19 microjoules of energy is, if you go across a carpeted floor and you rub your feet across that floor and you touch a piece of material, that amount of static electricity that you've built up just within your shoes and walking across this floor is enough energy to actually ignite hydrogen. So thank goodness you're not walking in a hydrogen environment. This is one of the things when everybody's talking about using hydrogen as the fuel of the future, one of the things that people need to remember is that hydrogen, because it doesn't take an awful lot of energy to ignite, we have to be extremely careful about it. The other thing about gases and vapors in particular that we also have to take into consideration from an EX perspective is as I mentioned, the minimum ignition energy, right? And we just mentioned about hydrogen, it doesn't take an awful lot of energy. But there's also what is called the lower explosive limit and the upper explosive limit or flammable limit. And this chart is basically telling us in effect that propane has somewhere in between about 1 to 2% at the lower level to about 12% or so at the upper level. So if we have a release of propane into the environment and we only have, say, 1% propane in the environment, and we have arcing and sparking or all different kinds of issues, we haven't at that point created enough gas in that triangle to actually have an explosion. When we get above that level, that means we've got too much fuel. We can have an arc or spark. We're not going to have a problem. Most gases and vapors have that LEL, UEL of somewhere between 2 and 15%. That's generally the sweet spot. But hydrogen, if you notice, actually has a lower flammable limit of somewhere around 10% to about 76, 77%, meaning that any time that we release hydrogen into the atmosphere and we combine it with air or oxygen, and if it's within that ratio, and we have 19 microjoules going off in some way, shape, or form, we're going to have an explosion. So this is one reason why we treat hydrogen slightly different than some of the other flammable gases and vapors in industry. So let's see this. Is it a poll? I think so. Oh,
yes. Let me share the question. We are going to check whether we are getting the full attention of the participants.
See if you were paying attention in the first part.
So we are asking you what is the definition of flashpoint, which was given before by Bob. Let's see if all is clear so far. So we give some time to provide click. You win nothing, but you even don't lose anything. So don't be shy.
Yeah, we're not keeping track of who answered what question right or wrong. So, and by the way, there was a question that was raised about zone division mapping. So we'll talk a little bit about that at the end because it is a good question. And speaking of which, the zone concept, which we're going to talk about, is primarily, again, that's an international concept. Here in the United States, we actually have two concepts. We have division and zones, and we'll talk a little bit about that at the end.
Okay, I stopped the poll and I share the results, and I'm asking you to comment.
Yeah. So, okay, the correct answer is that temperature in which flammable liquids will turn into a flammable gas. So remember, ignition temperature, that's that temperature in which something will spontaneously ignite. So sometimes people get the two terms confused, and that's okay. But just remember, flash point is that temperature in which a liquid will start becoming a flammable gas. Ignition temperature is that temperature in which something will spontaneously ignite. And by the way, most flash points are usually very, very cold temperatures. Most of them, they're usually below 0 degrees centigrade. So generally, we have to liquefied natural gas is one that we actually liquefy it so we can transport it, right? But we can keep it below its flash point if we keep it extremely cold temperatures. So transporting liquefied natural gas in large tanks, as long as we contain that tank, hey, we're A-okay, because again, it's way below its flash point. And again, if we took and ignited something on the inside of one of these big LNG tanks, there's too much fuel and it's below the flash point to where there's no flammable gas. Now, obviously, if we have a release into the atmosphere, that changes the subject completely. So, all right, close this and we'll continue on. Another factor that we have to take into account from electrical and mechanical equipment is the T class, and this is temperature classifications. So every gas and vapor out there, flammable gas vapor, we assign a T class to it. So if we see a gas that's a T1 gas, that means that the ignition temperature of that gas is above 450 degrees C. If it's a T2 gas, it's somewhere between 450 and above 300, and so forth and so on. So here's just showing some of those gases and vapors that we talk about. Notice hydrogen. Again, I had mentioned this earlier. Hydrogen has a very, very high ignition temperature. So we consider that a T1 gas. Some of the other gases you'll see that will range anywhere from T2, T3, T6. There's only really one gas that I'm familiar with that is T6 gas, and it's carbon disulfide. And it has an ignition temperature of 90 degrees C, which is very, very, very low. So we really need to be careful with carbon disulfide. Most of your flammable gases and vapors will have an ignition temperature of somewhere between T3, T2, and T1. That's generally about 98% of the gases and vapors in industry are going to be T3 or hotter. So as a generality, when we start looking at electrical equipment to place in this area, if we can find electrical equipment that's rated T3 or better, generally they'll be good for almost all applications. So this chart can be a little bit confusing, and I'll just try to explain it maybe a little bit. But basically, when we're selecting electrical equipment or mechanical equipment from a T code perspective, what we're trying to do is that we find a product that will have a T code that will correspond or be better than the T code of the environment in which we're placing it. So as an example, if we have a product that has a T4 rating, and if we look at our chart on the right-hand side, a T4 means it's 135 degrees C. That means under its maximum ambient rating of that particular product, the relevant surface of that product will never exceed 135 degrees C. So we know that from a testing perspective. We tested it, we put it in its maximum ambient. There we go, we have a number. A T4 gas is actually a gas that will have an ignition temperature above 135 degrees C, and it would be something below 200 degrees C, because if it was 200 degrees C or above, it would be a T3 gas. So a T4 gas could have an ignition temperature of, say, 140 degrees C. A T4 product could have a maximum relevant surface temperature of 120 degrees C. So we're saying from a temperature standpoint, a T4 product is suitable for a T4 or higher environment, meaning that in a nutshell, a T4 product can be used in an environment in which we require T4, T3, T2, or T1. Okay. Another factor that we have to take into account, especially when we're doing area classification, is the density of the gas. So all gases and vapors have various densities. We use air as a reference point of 1. So if you can see on this chart, you see gasoline vapors are much heavier than air. That's 4 times as dense. Propane is heavier than air. You notice on there that certain gases and vapors like acetylene have the same density as air, hydrogen being lighter than air. One of the reasons why acetylene is difficult to deal with is that if we do have a release of acetylene into the environment, it will basically go everywhere. It won't go up to the ceiling. It won't just get dispersed. It'll go all over the place. Gasoline vapors, generally our most flammable environment is right around our feet. So when we're fueling up a vehicle, people seem to think that vapors are actually going up, but they're actually going up and then dropping down. So the most flammable environment is actually around our feet when we're at a fueling station. So when we're selecting, say, for example, something to determine where the sources of release, and by the way, where are the sources of release that we normally would find in hazardous areas? Typically piping. Anywhere we've got a valve of some sort where we're bringing 2 pieces of pipe together, that's a potential source of release. That's an area in which a gas or vapor could escape under certain circumstances. So using this scenario, where would we place the gas detectors? So if the gas detectors were in an environment in which they were heavier than air, we'd want to put the gas detectors down near the floor. Obviously, in a situation where if the gas was lighter than air, we mount our gas detectors near the ceiling. Obviously, if it's an environment where acetylene is located or something like that, we would probably have our gas detectors located in a particular area that reflects the density of the gas, right? So there's some little things that we want to do when we're starting to design our systems around EX to make sure that we're taking into account the density, T codes, ignition temperature, and all that good stuff. So we have another poll question.
Yes, let me share the question so that people can.
And this is going to be tough because I didn't cover all the T codes, but I did give you a hint, and I will give you a hint. T4 is 135 degrees C. So the question really is, again, what would be the T code for a product that has a maximum relevant surface temperature under normal or fault conditions of 125 degrees C? So I'll give you some more hints here. T6 is 85 degrees C. T5 is 100 degrees C. T4, as I mentioned, is 135 degrees C. T2 is 200 degrees C. Excuse me, T3 is 200 degrees C, and T2 is 300 degrees C. So if that helps you a little bit.
Very good. We have a good response rate. So let's wait just a few other clicks. Then we can now stop the poll and I share the result for further comments. Here we are.
Yeah. So the majority of you said T4, and that is the correct answer because T4, remember, just going back in my last discussion, T4 stands for 135 degrees C. That means that a product that is rated T4 cannot exceed 135 degrees C. And in this case, this product is rated at 125 degrees C. So therefore, that would be the T code that we would assign this particular product. So that's when you see T codes on labels, and we'll show some labels here a little bit. that's really what is important also to consider, is understanding what the temperature code requirements are for the gases and vapors in your environment, and compare versus the electrical or mechanical equipment that we're putting in there. So continuing on, a little bit about area classification. And I'll kind of go through this really quick, but the 60079 standards, 10-1 deals with gases and vapors, 10-2 deals with dust. We also have other documents that are out there, the Energy Institute IP15, which is a wonderful document for area classification. Here in the United States, we have API recommended practices, and there's also an NFPA document. There are other area classification documents out there, but basically this is what we use as our documents to determine whether or not an area is hazardous or non-hazardous. And then once it is hazardous, then we need to determine whether or not what type of hazard it is. Is it a gas? Is it a dust? And how prevalent this gas or dust could be in that environment. So this is where we get into either zone 0, zone 1, or zone 2. So a zone 0 environment is an environment in which a flammable gas air mixture could be present continuously or long periods of time. Zone 1 environment is an area in which flammable mixtures can be present during normal operation. Zone 2, it's which it can be an explosive atmosphere, but if it does, it's for very short periods of time. So for talking about division and zone mapping, if you will, this doesn't show division, but basically under the US, the division concept incorporates both zone 0 and zone 1 as division 1 for the most part. Division 2 is basically the equivalent, if you will, of zone 2 environments. Okay. Now, there's category designation that I won't spend a lot of time on, but basically what you're seeing there, under the ATEX directive, we actually put down categories. So for example, if we had a zone 0 environment, we say that's equipment category 1G. You'll see on this little chart, and I'll see if I can actually highlight that, so to speak. So zone 0 is considered to be a 1G equipment category. Under the IECEX requirements, we call that a GA for what is called equipment protection level. So basically, if you can remember this, 1G and GA basically mean one and the same. This is the IECEX designation, and this is the designation under the ATEX directive. So marking of products, you'll find this type of marking on a piece of equipment that's ATEX certified. This is the type of marking you'll find on products that are IECEX certified. Okay. This is important when we talk about protection concepts of fault tolerance. So when we're talking about products that we can put into a zone 0, we say and we demand that these products must have 2 fault tolerance. So when you look at, for example, a GMI intrinsically safe barrier, you'll actually notice that there's 3 Zener diodes. There's actually redundancy built into within IS barriers, either a Zener or galvanically isolated barrier. So these have fault tolerance built in. That means that if there's a failure, it'll fail in a fail-safe mode. Single fault tolerance products are suitable for zone 1. General industrial products that will not cause arcing or sparking but have no fault tolerance are suitable for zone 2. And again, this is the equipment category where the IECEX references equipment protection levels. So I think this is our last poll question, and we'll, because I know we're starting to kind of run behind, and I'll zip through.
It is not the last.
We've got another
last. We have another one later, so people have to give us full attention for a few slides again. So here now the chance for you participant to provide your feedback on this.
Yeah, I think I just talked about this. So Let me rule out one, and nobody has answered this, but D, place where a dust hazard atmosphere is present. I think I got it covered up with my little polling thing here. Occasionally during, let's see, normal operations. So it would not be a dust hazard, because dust hazard, it'd be a little bit of a trick question. It would say zone 21. And since we're talking zone 1, that's actually a gas hazard. So the equivalent zone 1 from a dust perspective, we would classify that as a zone 21. A zone 0 from a gas standpoint, from a dust standpoint, would be zone 20. So for some of you who are involved in dust hazards, again, we're not talking zone 1, 2, and 3. We're talking zone 20, 21, and 22. So D would not be the correct answer.
Good. I think we have today a good response, a good participation to the poll. So I stop here and I share the results for further comments. Looks like
a vast majority of you got it right. Yes, correct. So basically A would be is frequently or continuously, we would consider that to be a zone 0. B is the correct answer, where it's present occasionally during normal operation. That's considered to be a zone 1. C would be basically the definition for a zone 2. So good job. All right. Now let's get into the protection concepts, and I'm not going to read that little chart, but basically the important thing to remember here is this information here. 4 main categories. Every piece of EX equipment that's built out there is going to follow one or more of these concepts built into that product. It's either going to be energy limiting. We're going to consider it to be non-sparking, such as increased safety. We're going to contain the explosion. Flameproof is a good example, or separation, such as pressurization. So all of them work in different fashions. They all work fine. They all have advantages and disadvantages, but that's really the key thing. So when we're talking about protection concepts and we're looking at products out in the field, we want to make sure that these concepts, once they're applied, are still operating and doing exactly what they should be doing. So energy limitation, again, what we're talking about here is primarily intrinsic safety. We're limiting the amount of energy below that minimum ignition energy for that particular gas group environment. And we divide these into different fault tolerance. So we'll have barriers that are suitable for IA, meaning that they're suitable for output into a zone 0, IB, suitable for zone 1, or IC, suitable for zone 2. Most of your barriers that you will find from manufacturers out there are actually rated EXIA. A vast majority of them are. Non-sparking, here we're taking products and we're basically saying, hey, there is no sparking that is going on here. How can we make sure that there's not going to be any sparking? So therefore, we build equipment in which there are very well-defined creepage and clearance distances between termination points. So terminal blocks, if all we're doing is putting a bunch of connection points inside of a junction box, this is a prime example of increased safety. So we can take this concept and put it into a zone 1 area because we're not concerned. There is no arcing or sparking going on. All we have to be concerned with really is the temperature code, how hot this product will get when placing it into a hazardous area. So it's a very effective way of dealing with hazardous locations. This is called EXE. A secondary one, it used to be called EXNA, is now changed, and now that's called EC. The old legacy one is now EB. So non-sparking is a prime example, increased safety. Containment, this is the one where we talk about heavy cast flame-proof type enclosures. So we're allowing a gas or vapor to get on the inside of these enclosures, and we're going to assume that there's going to be electrical arcing and sparking equipment on the inside. And if we have that right combination of fuel-air mixture getting on the inside of these enclosures, we're going to have an explosion. That explosion should be contained. We want to make sure all the bolts are nice and tight. We want to make sure that there's flame paths are nice and clean. We want to make sure that all the holes are plugged up with suitable plugs We want to make sure that the cable glands that are going in there are suitable to contain that explosion. So that's how flameproof works. We have an explosion on the inside and making sure that it cools that hot flaming gas, excuse me, to where it does not ignite the gas on the outside. There are other devices that are flameproof that you can actually go flameproof with really, really small devices, excuse me, in which they can be made out of plastic. So there are different devices that you can actually do that are outside of the big heavy cast flameproof type products, excuse me. Lose my voice here. The other one is separation. So this is where we're pressurizing something, or we're encapsulating it, or we're hermetically sealing it, or we're oil immersing it, or even restricted breathing. These are all basically trying to keep any flammable gas air mixtures from coming into contact with any potential arcing and sparking or ignition capable equipment. So as long as we can keep that flammable gas outside of our pressurized cabin, a restricted breathing enclosure, or immerse it in oil, these are all ways in which we're separating that fuel from coming into contact with the ignition source.
Excuse me, Bob, but we have a couple of questions.
Yeah.
It's better you read it because maybe I lose something.
Sure. Yeah, so one of the questions was for dust hazard environments, can we use flame-proof, explosion-proof devices? Yes, to answer your question, explosion-proof equipment here in the United States is suitable for a Class 1, Division 1. Oops, let me mute that one, sorry. For explosion-proof applications, explosion-proof boxes are rated for both gas and dust hazards. EXD boxes that are flame-proof are almost always rated as well as suitable for dust hazards. You always need to check with the manufacturer, but the way you'll see a marking, you'll see it, and we have a marking string here that I'll show you in just a second on a flame-proof box that will show EXTD. So TD is the protection concept, which basically means dust tight, and a flame-proof box is in effect dust tight. Second question, there was a question on 316 stainless or brass cable glands. Is there an advantage, disadvantage? I will tell you, I mean, we sell EX equipment, and most of the time, 98% of the time, we don't sell a stainless steel version. Most people will not use a stainless steel because generally speaking, stainless steel cable glands are a factor of 4 over the cost of, say, a brass cable gland. Meaning that if a brass cable gland is $20 US, a stainless steel version is going to be about $80 to $90 US. So it's a significant increase in price. What I do recommend to people is many manufacturers now will put a nickel plating on their brass cable glands. Nickel plating provides extremely good corrosion protection. Brass does to an extent. Brass actually, just standard brass, putting it in a corrosive environment, it will tarnish extremely quick. It'll become very black, brown, gray. But when you actually open up the gland and look at the inside of it, even glands that have been installed 10 years or so ago, they're very shiny, very clean. You don't see a lot of problems with pitting. Lastly, there was what can a separation method be used for zone 1? Yes, it can. Separation, as I mentioned, was things like pressurization. You can use EXPX is a pressurized method suitable for zone 1. PYB is also a pressurized method suitable for zone 1. So yeah, you can do separation using some of these protection concepts. Oil immersion is also suitable for zone 1. So yes, to answer your question, yes. So just to go through this real quick, show you the markings. So this marking that you see right here is all to be in compliance with the ATEX directive. Must have a CE mark. This number is the notified body. This is our EX hexagon or epsilon. This is telling us it's for surface industries or equipment group. Roman numeral 1 is G1 or 1G is telling us it's suitable for zone 0. Then this here, this marking string is actually our protection concept string. So in this case, this is an intrinsically safe device that's located and suitable for all gas groups with a temperature code of T4 or greater. And this EPL is telling us in another way that it's also suitable for zone 0. This is not the marking, however, for an intrinsically safe barrier. This is the marking for the device that would be attached to the intrinsically safe barrier. And I'll give you an example of that here in just a second. So that's typically your EX marking string. So this marking string is actually off a GMI barrier. So you can look at it and it gets a little bit confusing, but we'll try to make sense of this. So what you're seeing with this first marking string right here is that if you can see this, this is telling us it's got some things in brackets, but if we focus right here, EXNA, that's telling us that this product can be installed in a zone 2 area. But these brackets here are telling us that the output coming out of this portion of the barrier is providing protection into potentially a zone 0 area. This is telling us it can be installed in a 2C gas environment and can be installed in a T4 environment. So the brackets that you see are parentheses, that's telling you the output information. The other information is telling you where you can actually install it. Okay, so that's where people get confused a little bit and looking at all these marking strings on a barrier. And you'll see this kind of repeated. Here's our dust requirements. Here's a mining requirements. This is also other certifications for other world marks. So there's lots of different markings on this. So we really need to focus our attention on exactly what marking string that we're trying to find. So this is going into a flame-proof box. This is that marking string that you'll find. So this particular box is certified both around the ATEX directive, and there's your marking there. And this is the marking, and by the way, this is the dust marking that you will find, TB. So this product is both flame-proof, DB, as well as dust-tight, TB. So it's good for dust hazards as well as gas hazards. Then when we clear that, right below it is our IECEX marking string. So here's our certificate number. Notice that this marking string and this marking string is identical. And then again, we have the same information down here as we have right here. The marking string for dust is the same under the ATEX directive and the IECEX cert. So the important thing to remember is that if we look at labels, we really want to understand what these labels are. And we've done some webinars in the past on how to understand these labels in a much clearer fashion. Unfortunately, we're running out of time, but this is a good example, these last two slides, of if you can go and look at those and understand those labels, that makes life a lot easier. Here's our last poll question.
Yes, about EX marking, very fresh topic. So let's see if still we have the attention of the person.
I will be honest, this is a really difficult question.
Yes, I was about to say the same.
But I want to at least give you some hints here. So this is our stuff that we have for ATEX, right? So let's just eliminate this because we're not asking a question from an ATEX or IECEX. So what does this mean? DB, that's telling us it's flame-proof. Okay. This IA is telling us that inside a flame-proof enclosure, it's containing associated apparatus. The flame-proof box can be located in a 2C environment, and so forth and so on. So I think I hopefully just gave you a lot of hints there of what the correct answer should be.
Still answers are coming slowly, but improving. Let's give them some.
And by the way, I'll ask another question here. What zone is this suitable for based upon what you see here? Well, there's some hints. This is telling us this is category 2, meaning it's suitable for zone 1 under ATEX. This here is telling us it's also suitable for zone 1 under IECEX. But this is telling us that the output is suitable for zone 0. So there's a lot of different hints in here that's telling us it's suitable for a particular zone. It doesn't come right out and tell you all of the it doesn't come out and just say it's good for zone 1, zone 0, zone 2. You have to understand the nomenclature. So
okay, I think now we can stop the time and we can share the result.
Yep.
This was the last question.
So you're correct. The majority of you got this right. It is a flame-proof. It is a flame-proof enclosure suitable for 2C environments, located in a zone 1 area, and it contains associated apparatus. We hear the term associated apparatus. That's a fancy term for, say, an intrinsically safe barrier, or it could be a relay or something like that. This would be the marking on the overall enclosure. Okay. So there you go. If you can understand that marking string, that's about, well, there's more onerous ones, but that's a pretty good one to have under your belt. So there is also an EX wall chart that GMI offers. We also have a functional safety wall chart. And again, now, and by the way, this is actually a little bit, this is actually from another presentation that I didn't correct. But remember, this 60079 standards is really the key one. The 80079 standards apply to mechanical equipment. So if you're involved in any mechanical equipment for use in hazardous areas, you really want to focus your attention on the 80079 standards. If it's electrical, you want to focus your attention on the 60079 standards. Okay. Let us go close this, and I will.
Yes, as mentioned in the beginning, we have now a small section where we collected the question, and we are providing you the answer to your question that we collected during the registration phase.
Yep, I need to find it real quick, and I will find it, and I will bring it up.
No doubt on that. And again, you will get through email, you will get both a presentation, including the question and answer. So, and yeah, let me repeat something that I was saying before. YouTube channel, you can get all these presentation, this one, as well as all the other webinar recorded on the several topics. Before Bob was mentioning the chart, we have the wall chart, we have about functional safety. We have also a wall chart about intrinsic safety or hazardous area in general, as well as we have also the so-called SEAL manual, which is a special book which is collecting all things about functional safety and the two relevant standards, 61508, 61511. As you, yeah.
I apologize. I'm getting it up. It's taking a second here, but I'm going to have it here just a second.
If you find it, okay. Otherwise, I can share from my PC. It's up to you.
Oh, I brought up the wrong one here.
Okay. Okay.
No, I've got it. I just have to bring it up here right now. I think I can display. Okay, and then hopefully if I can show my Zoom controls, I can share my screen. And
yeah, maybe before to start with Bob, with the 7 questions and the 7 answer we have. You may check. We have a question from the
a hybrid, yeah. So a hybrid mixture, which protection are suitable for this atmosphere combination of gas and dust? Actually, that's a great question. In the US, we do have what is called simultaneous hazard, because if we take a piece of equipment and we cake it in dust and then we put it in a gas environment, it's going to have different characteristics than if we just do gas alone or dust alone. So actually, within the IEC world, in the 60079 standards, in the very back of the -14 standard, there's a little passage that talks about a combination of gas and dust. But right now, the standards really only address certifying it for gas hazards, certifying it for dust hazards, but not the combination thereof. So there is a little passage within 14 that talks about hybrid, how you should treat equipment, and that's in the design standard. The 60079-14 is what you would want to look at. Okay, can everybody see my screen, hopefully? You see it,
I think so, because I see it.
You see it? Okay.
Yeah, so I see it very well.
So this was and I know we're running a little long. We don't have that much to cover, but we'll kind of get through this real quick. So one question that was brought up, how does the IEC compare with the NEC or Canada with regards to EX protection concepts? So very briefly, the National Electric Code is what we follow here in the United States, primarily for our hazardous location installations, although in the offshore market, it's slightly different, and we'll follow API recommended practices or the US Code of Federal Regulations. But basically, the National Electric Code is pretty much the benchmark, if you will. There are some protection concepts that exist within the NEC that don't exist within the IEC, but there are some very close similarities. Explosion proof, the concept is really the same as flame proof. There are some differences, requirements as far as testing of it. The standards are different, but it's the same concept. Pressurization is almost identical. Our standards for pressurization here in the United States are almost identical to the IEC standards. Intrinsic safety is another one where it's almost identical to the international standards. There are some NEC protection concepts that we do have. We have basically that's not specifically a cross-reference to an IEC standard. There is what is called non-sparking or enclosed and gasketed, and there's also what is called non-incentive. So these are 2 protection concepts really that are not really recognized, if you will, within the IEC world. And again, we follow either a division. However, since 1996 in the United States, we now can actually classify our areas using the zone concept, and we can also use the exact same protection concepts that other parts of the world are doing. There are some differences, however, as far as installation requirements and certification requirements, but it's the same concepts, if you will. Canada follows the Canadian Electric Code, which at one time also followed division and then introduced zone. But now Canada within the CEC is basically saying, hey, any new installations, you must now follow the zone concept as opposed to either hybrid mix and match division versus zone. In the United States, you have the option still to do legacy division or North American zone. How do we connect and use different EX concepts? And so this was a question with regards to EXE equipment in conjunction with EXI. So EXE, as we recall, is increased safety. Here's the important thing to remember, regardless of the protection concept. From an installation standpoint, the cable glands must meet the same protection method as the enclosure. In this case, if we had a flame-proof box, we want to make sure that our glands are flame-proof. If If it's EXE, we can use an EXE gland, but we can also use an EXD gland. Generally speaking, the only kinds of glands that you'll find in the market are going to be EXD. There's going to be a barrier or non-barrier. There's going to be EXE type glands, increased safety. And in some cases, you'll find what is called EXNR, restricted breathing glands. Those are the three types of protection concepts. You can use pretty much EXD glands on any protection concept. So within EXI, intrinsically safe, generally intrinsically safe is going to be installed inside a different type of enclosure. It's not that you're just going to take an intrinsically safe barrier mounted on a wall, or if the end device is intrinsically safe, we can use pretty much almost any gland for that application. So there is a little stipulation within the IEC standard, which is kind of interesting. If we actually have a simple device for intrinsic safety, the gland and the simple device do not require to be certified. So we can use a general purpose gland for a simple device on a single circuit for intrinsically safe. Again, for simple devices, non-energy storing. This was a question that came up: what EX concept should I use specifically for a natural gas facility? And that's a tough question. But natural gas, as we kind of talked about briefly with LNG, it is primarily methane. It's a 2A T1 gas, and TA is the least volatile of the three gases. T1 is a very high ignition temperature. So generally speaking, we can use almost any piece of EX equipment in a natural gas type facility. But there are some generalities. Increased safety would be suggested, again, for terminal enclosures, or maybe combined with other protection concepts. Intrinsically safe certainly is a great protection concept, very safe, very cost effective, would make sense for a lot of your instrumentation circuits. You are limited with on intrinsic safety, though. Generally about 1 watt of power or less is really where you can use intrinsic safety. Pressurization makes sense if we have, say, an analyzer shelter or a control building. Instead of making everything EX, we take the entire building and basically turn that into a pressurized building. That seems to make sense a lot of times. Flame-proof is certainly an option, but as we can see, it's usually heavy. Lots of bolts, we have to maintain it. We want to make sure those flame paths are nice and clean. So there's not necessarily one general protection concept that's always best for every application. But you know, don't limit yourself to one protection concept. What I always tell engineers, and when I do engineering and design work, I look at all the different protection concepts to try to find the best solution from cost, maintenance, delivery, price. You know, all of these factors should be part of your evaluation, if you will. This was a question that was asked. We have a piece of equipment that's rated 2C, but we wish to install it in a 2B plus H2 area. Is this okay? Yes, it is. Something that is 2C means that it's suitable for all gas groups. If you see a piece of equipment or an environment that's rated 2B plus hydrogen, it means that within that environment, we may have some 2B gases, plus we have hydrogen as well. So 2C equipment is suitable for every gas group. 2B plus hydrogen environment is pretty much, you're covered, okay? However, you also have to take into account what zone is it? Is it zone 0, zone 1, or zone 2? We need to know that. What's our temperature code, as we talked about? Is our ambient range of our equipment suitable? If products are not marked, their default is -20 to +40. I know in various parts of the Middle East, and certainly in South America and here in the Gulf of Mexico, we require +50 degrees C, and in many cases in other parts of the world, even higher than that. So we have to double check to make sure our equipment is suitable for those high temperature environments. And conversely, when we're doing in low temperature environments, is it below -20? I know we've worked on projects where the ambient was -40. So a lot of EX equipment is not suitable. And certainly things like ingress protection, certification, conditions for safe use. These are all part of your equipment that you have to check beforehand to make sure that they're suitable. Can I install an intrinsically safe barrier in a zone 2 environment? Yes, you can. As we kind of talked about a little bit, where we talked about a flame-proof box, an ISB in and of itself is suitable for installation in a zone 2. However, we do have to put it in a suitable enclosure. So we could put it in a sheet steel enclosure, and this would be the marking on that sheet steel enclosure if it was an increased safety. We'd have EX, EB, IC, and then output is IA, but yet the overall box is only suitable for mounting in a zone 2. However, if I need to go into zone 1, I could put it in flame-proof, which would be marked this, or we could put it in a pressurized enclosure, which would be marked this, and it'd be suitable for zone 1. Okay. Oh, got to clear my drawings. Close that. Here we go. I think we've covered this one already. Selection of equipment. I think we already did this, so I know we're running late. So we'll turn this back over to you, Mauro. You got it from here.
Yes. Thank you very much, Bob. Yeah, this slide, just to mention and just to repeat that we are still continuing in doing our live webinars, and this time we are also trying to innovate the topics. So let's follow us in our website, and you will have the chance to select further webinars. If you want to go back and to watch one of the old webinars or a subject that is not going to be repeated, you have all of them registered in our YouTube channel. So you have the chance really to spend hours and hours together with us. At any time you want, but of course, participating to the live webinar, you have the chance, to raise questions and to interact with us and with our expert. So, I would say.
Yeah, and Mauro, if I may add to that, we get questions. Obviously people ask questions during this, but then maybe later on you'll have a question or something like that. Please feel free to reach out to us. We're happy. I just got a question from somebody who watched a webinar from 3 months ago. They saw it and they had a question on it. So please don't hesitate to reach out to us if we can answer a specific question that you might have with regards to standards or applications or anything like that. Don't hesitate.
Yeah. And even if you have some, I don't know, some suggestion, recommendation of topics that you would like to see covered by a webinar, we are willing to collect these wishes, and if it is part of our knowledge, it's interesting, and we are willing to put together slides and to transfer our knowledge to our customers. So yes, very last question. Very last question. We would like to, we would like to know from you, to have your feedback about how we perform. Of course, this is be straight. Is a question on how Bob performed, because he was the guy saying the interesting thing, and even without waiting the answer, which anyway I will share immediately. It is already given. So I would like to thank you, Bob, very much. This is again another confirmation on the appreciation on your speech, on your transfer of knowledge, and thank you very much to all of you participants, which you decided to share with us this hour and 15 minutes. So we look forward to see you again to the next webinar. And I wish you all the best for the continuation of your day, your week. I will, for example, now start my evening. Yes, yes. And I have my wife already sending me a message whether she can take out the sparkling wine from the fridge. So I will reply her, yes, I'm done.
There you go.
Again, thank you very much to all and see you next time. Thank you, Bob.
Thank you, Mauro. Thank you, everyone.
Have a nice day.
Ciao.
Bye-bye.